Hey everyone, and welcome back to this class, the Numpy stack in Python. In this lecture, we are going to discuss dot products, which is a type of multiplication you can perform on vectors. Recall that we have two definitions of the dot product, and that they are equivalent. The first is the summation of the element-wise multiplication of the two vectors. Here I'm using D to index each component. Notice that the convention A transpose B implies that the vectors are by default column vectors, so the result is a 1 by 1, which is a scalar. The second is the magnitude of A times the magnitude of B times the cosine of the angle between A and B. The second method isn't really convenient unless we know each of the things on the right-hand side to begin with. In fact, it's more typical that we would use this to find the angle itself by equating the two methods. Including it in this lecture just lets us explore more features of Numpy, which is a good thing for you. So let's try this out in code. Let's start out with the two vectors 1, 2, and B is going to equal 2, 1. So suppose we were to use the direct definition of the dot product. You'd want to loop through both arrays simultaneously, multiply each corresponding element together, and add it to the final sum. So let's try this first. So for E and F in zip AB dot accumulate E times F. Okay, so the result is 4 as expected. But another interesting operation you can do with Numpy arrays is multiply two arrays together. Previously, we only saw how to multiply a vector by a scalar. So let's try A times B and see what that gives us. So we see that this gives us the element-wise multiplication of the two arrays, as one might expect. This also means you can't do this with two arrays that are different sizes. Now all we need to do is sum everything together. Luckily, Numpy has a sum function that allows us to do just that. So we call np.sum, and we pass in A times B. So that gives us the expected result. One interesting thing about Numpy is that the sum function is an instance method of the Numpy array itself. So an alternative way of doing this would be A times B dot sum, and that gives us the same answer. Finally, while both of these methods yield the correct answer, there is a more convenient way to calculate the dot product. Numpy actually comes with the dot product function, so we can call np dot A and B, and that gives us the expected result. Like the sum function, the dot function is also an instance method of the Numpy array, so we can call it on the object itself. So that's A dot B, and we get the same answer. This is also equivalent to B dot A. Now let's use the alternative definition of the dot product to calculate the angle between A and B. For this, we need to figure out how to calculate the length of a vector. Using only what we know so far, we can do this. It's just the square root of the sum of each element squared. So for example, A magnitude is equal to np dot square root A times A dot sum. So A mag is 2.236 as expected. Numpy actually has a function to do all this work for us, since it's such a common operation. It's part of the linalg module in Numpy, which also contains many other common linear algebra functions. So let's try that again with np.linalg.norm, and we pass in A, and we get the same answer. So now we're ready to calculate the angle. So the cosine of the angle is equal to A dot B divided by the norm of A times the norm of B. So the cosine of the angle is 0.8, and the actual angle is the arc cosine of the cosine of the angle, So the angle is 0.643. And this is by default in radians.